A narrative exploration of gravity's hidden depths. Most of us casually think of gravity as a mutual attraction between objects that possess mass. We stand on a scale in the morning, observe the number it shows, and accept that this reading represents Earth's gravitational pull on our bodies. But the moment we extend our perspective beyond everyday routines and look up at the cosmos, gravity becomes much more than a simple downward force. We envision the sun anchoring planets securely in orbit, and we marvel at how black holes exert an unimaginably intense draw on surrounding stars and gas. This leads us to believe that gravity is easily defined, a straightforward force that keeps us from floating into the sky. Yet recent scientific breakthroughs have revealed that what we traditionally label gravity is just the tip of a much larger phenomenon. In the modern era, thanks to Einstein's general theory of relativity, it has become increasingly clear that gravity isn't a mere force in the conventional sense. However, before diving into relativity, let's take a brief step into classic physics. We all know the legendary story of Isaac Newton, the 17th century luminary, often celebrated with an apocryphal tale about an apple striking his head. Although the dramatic version probably never happened, Newton did, in fact, witness an apple falling and grew deeply curious about the straight downward path it travelled. Why did it descend directly rather than veer sideways or fly upwards? His conclusion was that a force of mutual gravitation exists between any two bodies, and that this force is proportional to their masses, yet inversely proportional to the square of the distance between them. In short, he concluded that apples drop because they are accelerated earthward by gravity, which he regarded as a mysterious pull. Yet Newton himself reportedly suspected something was missing from his grand explanation. Early on, he even considered gravity to be more of a push rather than a pull, hinting that he had an intuition beyond the accepted model of his day. Regardless, for the next 4 centuries, his law of universal gravitation rose to near-biblical status among scientists, overshadowing hints that a deeper reality might exist. Then, in 1905, while working as a patent clerk in Switzerland, a young Albert Einstein emerged with revolutionary ideas that challenged Newton's perspective. Initially mocked or disregarded, Einstein's proposals sounded outlandish until observational evidence slowly proved them right. His key insight built on an earlier finding by Galileo, who showed that absent air resistance, all objects fall at the same rate, no matter how heavy or light. In a famous demonstration of this principle, Apollo 15-1, astronaut David Scott dropped both a hammer and a feather on the moon's surface, and they hit the ground at precisely the same time. The moon's lack of a dense atmosphere let us glimpse Galileo's notion in crystal clarity. The reason these two objects touch down simultaneously is that, in the framework of Einstein's relativity, they aren't truly falling at all. There's no force pulling them. Instead, they're following the straightest possible path through curved spacetime. From Einstein's vantage point, gravity isn't a force that drags masses together. It's the curvature of the 4-dimensional construct we call spacetime, shaped by the presence of mass. Without any opposing force, objects simply keep traveling in straight lines along these curves. To picture how this works, imagine a rubber sheet representing spacetime. When you place a heavy sphere, like a planet, on that sheet, the fabric bends downward, forming a gravity well. Any smaller sphere nearby naturally rolls toward the larger one's depression. The bigger the mass, the deeper the well, and the more other objects will seem pulled by it. Einstein realized that apples plummeting from trees and planets orbiting stars are simply objects following curved lines molded by mass in the space-time continuum. The heavier the object, the more pronounced the curvature. This curved space-time concept also illuminates why spacecraft use gravity assists. Engineers exploit the deep wells of planets like Jupiter or Saturn to slingshot passing probes, altering their speed and direction without expending large amounts of fuel. By grazing the edge of a planet's gravitational well at high velocity, spacecraft accelerate and arc off on new trajectories. An elegant technique proving that gravity, as Einstein described it, is indeed a geometric warping rather than just a simplistic pull. Moreover, Earth's gravitational influence extends far beyond its surface. Despite what our eyes might tell us, astronauts aboard the International Space Station, ISS, are not floating because Earth's gravity has somehow disappeared at that altitude. In fact, the gravitational force in low Earth orbit remains about 90% of what it is at ground level. The perception of weightlessness arises because both the astronauts and the station are in perpetual freefall around the planet, moving so rapidly that they continuously miss the ground. This state is referred to as microgravity, and it closely mirrors what would happen to any object drifting far from any major gravitational source, or to one plunging toward a massive body. Both experience the same apparent weightlessness because they share identical motion. Another remarkable illustration of curved space-time is gravitational lensing, which occurs when a massive cosmic structure, such as a galaxy cluster, bends the path of light passing nearby. From our vantage point, the light we see can appear distorted or multiplied. This lens effect, known colloquially as Einstein's lens, has offered astronomers the chance to detect galaxies and quasars hiding behind large celestial masses, objects that would otherwise remain invisible. Take the spectacular example of Einstein's cross. 4 distinct images of the same quasar circle a central galaxy that warps light coming from beyond it. This discovery proves how massive bodies can dramatically deform the very fabric of space-time, revealing phenomena previously tucked away by cosmic distances. Yet even with all these successes, Einstein's theory runs up against a stubborn challenge. It conflicts with quantum mechanics, the branch of physics describing nature at subatomic scales. Physicists seeking a unified theory of quantum gravity aim to integrate Einstein's curved space-time with the ghostly behaviors of particles and fields that quantum theory presents. So far, no universally accepted solution exists. Further complications arise when researchers examine conditions in extreme environments like black holes, where calculations break down. Observations from Sagittarius, the supermassive black hole at the center of our Milky Way, align with Einstein's predictions about redshifted light, but a comprehensive explanation of gravity in such intense fields remains elusive. For now, Einstein stands triumphant, but many scientists expect that, sometime soon, perhaps within the next decade or so, observations in extreme gravitational realms will reveal places where general relativity fails to offer a perfect account. At that juncture, a new visionary might step forward, akin to Einstein in the early 20th century, to provide the missing pieces in our understanding of gravity. Who knows? Maybe we won't have to wait another 300 years for that transformation in science to unfold. Ultimately, our theories must grow as we discover more about how space-time works under the strangest conditions imaginable. For Earthbound life, gravity can still be measured with a simple household scale. But in the cosmic ballet, gravity is a nuanced dance of curved geometry and relentless acceleration, bridging the gap between the orbits of planets and the swirl of galaxies. If you're excited about the next frontier, perhaps those radical leaps in our understanding of reality, keep watching the skies and remember that breakthroughs may occur just as unexpectedly as when an apple fell from a tree centuries ago. Share your thoughts. What do you think the future holds for our comprehension of gravity? Will we find that a new generation of scholars revises Einstein's theories? Or will general relativity stand until we crack the code of quantum gravity? Join the conversation below, and if this exploration ignited your curiosity, please give it a like. Stay tuned by subscribing, because we'll continue bringing you fresh insights whenever new discoveries push the boundaries of our cosmic knowledge. Here's to the next epoch of gravitational revelations. May they be as revolutionary as the day an apple made Newton ponder the forces that shape our universe.